Okay, so de Moivre's theorem, de Moivre's theorem is a way in which we can manipulate powers of complex numbers that are already in polar form. I guess the key element, the key component of the whole thing is if I raise any complex number to a power, well, if they're in polar form, all we need to do is raise the magnitude of the complex number or the modulus of it to the power of n and multiply that angle by n as well. So we can go through the proof and we might get around to doing that in class, but I guess in short, the nice application of it is if we think of cis pi on 3, that's cos pi on 3, which is a half plus root 3 on 2i. If we raise that to the power of 9, imagine how hard that would be, trying to expand that. In polar form, cis pi on 3 cis to the 9 is the same as cis pi on 3 to the power of 9, which means it's just 1, which is the magnitude to the power of 9, times cis 9 pi on 3, because 9 times pi on 3 is 9 pi on 3, which is 1 cis 3 pi, which in, if we turn 3 pi into the argument of z being between negative pi and pi, is cis pi, which means we're over here, which in turn is just negative I. So obviously it's a much simpler way to manipulate complex numbers. So we know that if we divide, we subtract the angles, but let's work out what the angles would be first. So this expression, the top, nothing really happens there. Denominator, cis pi on 3 to the power of 7 is the same as cis 7 pi on 3, which is 7 pi, let's undo that. It's 3 and 4 is 12, so 7 pi on 4 is 21 pi on 12, subtract 7 pi on 3, which is 28 pi on 12. So I get cis, what do I get? Cis negative 7 pi on 12. And negative 7 pi on 12 is in the domain that we're interested in, and so that's fine. The really big practical application of it is solving my complex equations, all right? And I guess the process, I think the easiest way, I guess the process is whatever the complex equation is we're trying to solve, we just convert both left and right hand side into polar form. So the polar form of z is just r cis theta, that's the left hand side. The polar form of 1 plus I is root 2 cis pi on 4. And so the left hand side now becomes r squared cis 2 theta equals root 2 cis pi on 4. And then what we do is we equate. For these two terms to be equal, it means r squared has to be the same as root 2 and 2 theta has to equal pi on 4. And then we find some solutions. So let's have a look. If z cubed is equal to 1, so again, z is the same as r cis theta, all cubed. 1 in polar form is 1 cis 0. Yeah, that gives me the point 1, 0. All right, so now the left-hand side, using de Moivre's theorem, that's the same as cis 3 theta equals cis 0. So now we equate expressions. R cubed has to equal, well, the number in front of cis theta is 1. So r cubed has to equal 1. And 3 theta, the angles have to be the same. 3 theta has to equal 0, but it's equal to 0 plus any 2 pi of that. Yeah, so it could be 0, could be 2 pi, could be 4 pi, could be 6 pi. There's an infinite number of solutions. So it's, in some ways it's a little bit like solving our trig equations. We have to think of the general solution. So clearly on the left-hand side, r is equal to 1. Here, theta is equal to, well, on the right-hand side here, I've got 2k pi on 3. So if I put k equal to 0, I get theta equal to 0. If I put k equal to 1, I get 2 pi on 3. If I put k equal to 2, I get 4 pi on 3. And then if I just say I put k equal to 3, I would get 6 pi on 3, which is 2 pi, which is back to 0 again. So I've already, and then I start repeating my solutions, which means I run out of room. Let's come up here, which means my solutions are going to be, well, r is 1 the whole time. So it's 1 cis, first angle was 0. Z2 is equal to 1 cis 2 pi on 3. Z3 is equal to 1 cis. Now 4 pi on 3, but 4 pi on 3 isn't in the domain that we're interested in. Negative 2 pi on 3. So if I cube any of those 3 complex numbers, I will end up with 1. That's what that's telling me. Okay? We can continue off the example 22 from the top right hand side. I didn't realise that one was there. So if I pick it up from that bottom line, r squared cis 2 theta is equal to root 2 cis pi on 4. Again, that means r squared has to equal root 2 and 2 theta has to equal pi on 4 plus some 2k pi. All right, so r squared is 2 to the half, so r has to equal 2 to the power of a quarter. Now we can tidy this up a fraction. If I take pi on 4 out the front, I get 1 plus 8k. Yeah, just think back to our trig equations, divide both sides by 2. So the only reason I do that, and it's not crucial. Now, if I put k equal to 0, I get pi on 8. If I put k equal to, now I'm going to go with negative 1. Oh. If I put k equal to negative 1, simply then it'd be in the domain, I get 1 minus 8, which is negative 7 pi on 8. If I just put k equal to 2, I get 17 pi, if I put k equal to 1, I would get 9 pi on 8, which is outside my domain, so I know I'm going to have to go back the other way anyway. So my solutions are Z1 is equal to 2 to the quarter cis 0. Z2 is equal to 2 to the quarter cis negative 7 pi on 8. Okay, so it's just a gradual process. You know, we're covering a fair chunk of the complex course over this little period. So it's just stick to the process, left-hand side, write it as write everything in polar form, and everything's a little bit easier to manipulate. All right, so let's have a look at some other sort of applications for it. Let z equal a plus bi, where a and b and z squared equals 3 plus 4i. Find by equating in terms of a and b. Find the equations in terms of a and b by equating real and imaginary parts. In other words, take the steps to solving the equation. So we're going to approach it in a different way. So if I want to use a factored process, if z is equal to a plus bi, z squared is equal to a plus bi squared. So z squared is equal to a squared plus 2abi plus bi squared. I'll put it there, plus b squared I squared, I should say. So z squared is equal to a squared minus b squared, which is the real component, plus 2ab, the imaginary component. That's got to be equal to, z squared is also equal to 3 plus 4i. Therefore, the real components, a squared minus b squared has to equal 3. The imaginary components, 2ab has to equal 4i, which means ab is equal to 2i. Oh, sorry, the I shouldn't be there. It's only confusing. So I'm just equating the imaginary components. Yeah, 2 equations, 2 unknowns, I can solve that. I sometimes think the easiest way to solve this is to square both sides here. So we're up to part B now. So part B, if I square everything in that equation there, I get a squared b squared is equal to 4. And from equation 1, I get a squared is equal to 3 plus b squared. Yeah? So now I can substitute a squared in. B squared outside of 3 plus b squared equals 4. So I get b to the 4 plus 3b squared minus 4 is equal to 0. So again, if I put u equal to b squared, u squared equals b to the 4. So I could rewrite this as u squared plus 3u minus 4. So that factorises u plus 4u minus 1. That looks right. Equal to 0. Therefore, u equals negative 4, u equals 1. Now u is actually b squared. So I can write b squared equals negative 4. B squared is equal to 1. Now, if we were to solve this, we would say b is equal to plus or minus 4i squared, take the square root, 2i, and b is equal to plus or minus 1. Now, key thing to note here is, up the top, a and b are elements of R. So a and b are real. So they're not valid solutions. So therefore, b is equal to plus or minus 1. So if b is equal to 1, a is equal to, what was a equal to? Well, over here we'll do a is equal to 2 on b. So if b is equal to 1, a is equal to 2. If b is equal to negative 1, a is equal to negative 2. So my solutions, therefore, z1 is equal to 2 plus I, z2 is equal to negative 2 minus I. Okay, so that's obviously we solved a very similar problem, previous example, by using de Moivre's theorem. We have an alternative available to us, and really it's only ever going to work for z squared is the only time I would try it. I wouldn't be trying it for anything greater than a squared expansion because it gets messy. All right. Again, these questions are written here because we're sort of chewing a lot of content out of the Year 12 book. So I want you to have a go at this stuff and, you know, take your time with it. We've got lots of time to get through it.